In this video, we work a few problems from the end of section 5.5. I actually have a set of problems here, and they're all related to finance, money. So here's our first problem. It's exercise 87. It says, when the annual rate of inflation averages 5% over the next 10 years, the approximate cost of goods and services during any year in that decade is given by C of t, where t is the time in years and p is the present cost of whatever it is you're purchasing. So that C of t is some present cost times that 1.05 because of that 5% raised to the t power. So basically that just says after 1 year, the price is expected to be 5% higher than it was previously. And then in part A, it says, the price of an oil change is $24.95. Obviously, this seems to be a very dated textbook. I don't know when it was published, but the price of an oil change being $24.95 is it's an inexpensive oil change. I think it was like $30 in the 90s. And it's been a long time since then. It says estimate the price 10 years from now. Well, assuming that that price is initially $24.95, we can just evaluate this function at t equals 10. And that's going to give us the price of the oil change 10 years from now. So I've got a slider here for my p-value. And we've actually graphed the function c of t. So c of t is this function right here. It looks just like a traditional exponential function. That's exactly what you would expect. But the base is 1.05. And then we're multiplying by this extra factor of p, which is the present cost of your product. So we can see we evaluate this function at t equals 0. We get c evaluated at 0, that's p times 1.05 raised to the 0, which is just the present cost. So the present cost is always our y-intercept for that particular product. And then we can answer the question, what is the price of an oil change 10 years from now? Well, it's just c evaluated at 10, or $40.64. So let's say, how would we do that with pencil and paper? Well, we would just have c of t, or we would have c of t equals $24.95 times 1.05 raised to the 10th power. And then we would simplify that. We would usually just type it into a calculator and simplify, and we would get that number. And we see that that's the same value that the Desmos calculator gets when we just evaluate c at 10. This is what we would typically write down on paper, and then we look at our calculator and see it's about $40.64. So the price of an oil change went up approximately $15, $16 in 10 years, according to this model. Okay, and then it asks us to find the rate of change of the cost with respect to time at t equals 1 and t equals 8. Now, what we have here is p, which is just a constant, times a to the t, and we have that differentiation rule. The derivative of a to the t, or the derivative of a to the x with respect to x is natural log of the base times a to the x. We've talked about that rule, we've derived it. So when we take the derivative of that c of t equals some constant, p, times 1.05 raised to the t, the only difference between the original function and the new function is that we were multiplying by that natural log of the base. So c prime is just p times natural log of the base, which is 1.05, times the original exponential function. And then if we evaluate at t equals 1, we get 1.278 approximately, or 1.28. And then if we want to, we can just look at what this extra factor is, ignoring p for a moment, and then saying this is natural log of 1.05 times 1.05 raised to the first power. And I chose to write that 1.05 to the first in front of the logarithm. So I've got that right there. So it says, okay, it asked us for the rate of change. We computed the rate of change and we plugged in t equals 1, and we will substitute t equals 8 as well. But I always like to interpret what it is we're finding. This is giving us the rate of change of the cost of that product with respect to time at time t equals 1. So that's saying, what is the rate of change of cost? How much is our cost increasing at 1 year from now, provided that this model holds, provided that we've got that 5% inflation rate. Well, according to that, our cost is increasing at a rate of 1.05 times the natural log of 1.05, which is 0.05 approximately, times the present cost. So the rate of change is actually like basically 5% of that present cost. It's a little bit more than 5% of that present cost. So I've written that in a paragraph here. It says changing cost with respect to time is 1.05 times the natural log of 1.05 times p, which is, again, just approximately 5% of p. So the cost is increasing at a rate of 5% at time t equals 1 per year. It says time t equals 0, but t equals 1 per year. And then if we use the price of an oil change, and we're actually taking that 1.05 and multiplying it by that $24.95 price of an oil change from the textbook, which I'm like, I don't know when that number was current, but at some point that number was current. If we take 5% of that $25, it seems like the rate of change is a 1.28 approximately. So basically what we're saying is that if the original cost was about $25 for that oil change, then 1 year from now, we would expect the cost to be increasing at $1.28 dollars per year, or $1.28 per year. And we can do the same thing at t equals 8. And so we say, okay, we evaluate at the same function, but now instead of plugging in t equals 1, you plug in t equals 8. So our function was p, and then you multiply by the natural log of 1.05. And then you multiply by that 1.05 raised to the 8th. Because basically what you're doing is you're imagining every year we multiply by 1.05. The price goes up, the price 1 year from now is 1.05 times last year's price. So it's original price plus the 5%. And then you say, well, what is it going to be the year after that? Well, it's the price that it was this year times 1.05 again. So you have that p times 1.05 from last year, and then you multiply by 1.05 again. So you have p times 1.05 squared. And so every year you're multiplying by an extra 1.05, again, multiplying the original price by like 1, which is giving you the original price plus that 0.05, which is giving you that extra 5%. So the price is increasing 5% a year, and we just keep multiplying by this 1.05 each year, and that tells us how the price is changing. So then we evaluate at a particular value of t, and we get this 1.798 number, or if we round, it's $1.80. So it's saying for that oil change would start it at $24.95. The rate of change 8 years from now for the oil change is expected to be $1.80 per year. So we'd say, okay, what is the actual price 8 years from now? Well, according to our model, if we had that 5% increase every year, then 8 years from now, the $25 oil change will become a $36.86 oil change. And you say, okay, well, what's it going to be next year? What's the rate of change with that? It's $36.86, but how fast is that price increasing? Well, it's increasing at $1.80 per year at time t equals 8. That's what that C prime means. All right, then question C says, verify that the rate of change of C is proportional to C. What is the constant of proportionality? And we can look at C prime and look at C. And I think it's relatively obvious that C prime and C are basically the same function. So there's our C prime. And C looks just like it, but it doesn't have the logarithm. Because remember that logarithm came from taking the derivative of a to the t with respect to t. And if you graph C prime, sorry, it's got another function there. If you graph C prime, you can see the difference between C and C prime. So they both have the same basic shape. You zoom out, they're both exponential functions, but multiplying by that log of 1.05 makes this one have much smaller function values. It looks like the whole graph has been shifted to the right. You don't want to think of it that way. You want to compare the y values in a particular year. So you say when t equals 1, I'd like to compare the y value for c prime to the y value for c. And we see that there's a big difference between those y values. That factor that gets you from c of t to c prime of t is that natural log of 1.05. So these y values are actually proportional to each other. This y value times natural log of 1.05 will always give you this y value. And so they ask us, they say, verify that the rate of change of c is proportional to c, and we see that's true because you've got c prime equals p times 1.05 raised to the t. That's actually our c. If we wanted to, we could call that c of t times the natural log of 1.05. And that's not something that Desmos will be able to graph. That's a differential equation. It says c prime is equal to this constant times c. What is that? What is c equal to? Or what is c of t? What is the function c of t? And it turns out that c of t is this present cost times the 1.05 raised to the t. So the constant of proportionality is natural log of 1.05, which is approximately that 0.0487. So if we take the y values on this graph and we multiply by that natural log of 1.05, we're basically multiplying the y values by 5% or 4.87% to be exact. I'm going to take that and then 1.05 to the t. Okay, so there's our c prime function. Now when I saw that, when I computed the log of 1.05 and then I noticed that it was very close to 5%, I was curious about the relationship between the natural log of x and its value near x equals 1. So like, what is the relationship between the natural log of a number and like the value of that number? I don't know how maybe I'm not explaining it very well. Basically, what's the relationship between the input value, this x value that we're putting into the logarithm, and this output value? And I was like, that's 1.05. We're taking the log of something that's like basically 105%, and we get 5%, like, or in decimal form. Like, I wonder if that's always true. In order to figure that out, all I did was graph the logarithmic function. And actually, if we graph the natural log of x in the same graph, we see that's the inverse of our exponential function. Now it doesn't look like the inverse of this one because the base is different. This is a logarithm with a base e. This is an exponential with a base 1.05. I'd like to actually get rid of that first function. Let me examine the graph together. So, okay, well, what's the rate of change of that? We know that f prime is 1 over x. And if we want the equation of the tangent line, it's just the function value at x equals 1 plus f prime at x equals 1 times x minus 1. But we can tell that f prime at x equals 1 is just 1 divided by 1, which is 1. So the slope is 1. And we know that natural log of 1 is 0. So basically we have 0 plus 1 times x minus 1. So y is actually equal to x minus 1. Or in other words, natural log of x, that's our original function, is approximately equal to x minus 1 when we're in the vicinity of x equals 1. So if I want to, I can zoom in a lot on my natural log function. That's what the natural log of x looks like. Then we can graph y equals x minus 1, and we see that they're approximately equal to each other. And if that's the case, when I am looking at the natural log of 1 plus the interest rate, according to this, the natural log of 1 plus the interest rate is 1, or is that 1 plus the interest rate minus 1, approximately. Well, what's 1 plus the interest rate minus 1? Well, the 1's cancel and you just get the interest rate. So the log of 1 plus the interest rate is approximately equal to the interest rate in decimal form. So that's kind of cool to see. I was like, I think that that's the relationship just because I saw that, this natural log of that number and that number. And now we verified it by looking at that tangent line approximation of the function. Sometimes we call that the linear approximation of the function. It's the same thing as it's just a tangent line, but we're thinking of it as a function approximating the original function. So we're saying as long as we stay near x equals 1, this is a pretty good approximation of this function. Now, we weren't asked about inverse functions, but I thought it might be, or actually maybe we were asked about inverse functions. I don't remember what the original problem statement said, but the estimated, this function that we were given is the estimated cost of some particular product. Let's say a product or service with price P after T years, given an average annual inflation rate of 5%. And that's given by this function. I had to add some subscripts in order to graph it. We should zoom way out for this. And then if we want to, we could plot that point. When T equals 0, we get the beginning price. And I'm still using that beginning price of $24.95 for that oil change, which is, again, probably dated information. Now, for asked to find the inverse function, typically what we do to find an inverse function is we solve for the independent variable, and then we switch the roles of x and y. Now, if we solve for the independent variable, all we're doing is writing the equation of the original expression, or we're writing the equation in a different form. So if I have this equation and I'm trying to get t by itself, and I've written t sub 1, but what I really mean is t, and I've written c sub 1, but I really mean is c. So the cost as a function of the number, the present cost of the product as a function of the number of years since we, initially measured that cost or that price is equal to the price right now, or the price at time t equals 0 times 1.05 raised to the t, where t is the number of years since it was that price p. So when we graph that, we see at time t equals 0, we get the original price. If you want to, you can solve this for t. Instead of writing this dependence c of t equals p times 1.05 raised to the t, you can sort of drop the dependence on t and just think of c as equaling p times 1.05 raised to the t. I think I'm just going to solve this on paper with you, and then we'll talk more about it in just a moment. Now, if I solve for t, well, if I want to solve for t, the first thing I would do is divide both sides by p. So what I get is the cost t years from now divided by the price right now. And that's equal to 1.05 raised to the t. And then you might say, okay, I'd like to get rid of this exponential function with base 1.05. How do I get rid of it? Well, we just take the log of both sides, but we have to take the log with the base 1.05. Or we don't have to, but I have a tendency to choose to. If we're thinking of undoing a to the t, we undo a to the t with log base a of t. So you've got log of 1.05 divided, or log base 1.05 of c divided by p equals log with base 1.05 evaluated at 1.05 to the t. So those are equal to each other, but then again, because this function and the corresponding exponential function undo each other, we get just a t on the right-hand side. So t is equal to log base 1.05 of c divided by p. You say, okay, well, what does that mean? Well, t is the number of years. What should I say? The number of years. I'm having trouble with my English, at which the product of price P will be, how do I say this? Okay, so I actually peeked at my own answer from last time. Sorry, my paper is starting to fly away. So I had to put my watch over here. It says T is the number of years at which the product of price P, let's say at time T equals 0, will cost C dollars. So we're assuming that we know the price, and we know the cost, and this will give us the number of years when the product with price P right now will cost whatever C is later. So T is actually a function of C. All right, so if I look at this graph of C of T equals P times 1.05 raised to the T. So C of T equals P times 1.05 raised to the T is just an exponential function. And it looks like this. Looks like all the other exponentials. Now when T equals 0, we have got P times this number raised to the 0. Any number raised to the 0 that's non-zero is 1. So this is just going to give us P at time T equals 0. So that's the cost at time T equals 0. And then this is the cost T years later, provided that we have that 5% inflation rate. So at T equals 1, this value is supposed to be P, well, T equals 1, and the Y value on this graph is P times 1.05. So it's the original price plus an extra 5%. And maybe it's better to write that as 1 and 1.05p, just to emphasize that we're multiplying those. This kind of looks like a function, so we want to be careful about that. This is multiplication. Now, technically, this equation actually just is a rearrangement of this equation. It's as if I took C equals P times 1.05 raised to the T, and then when I solved for T, I got T equals log base 1.05 of C divided by P. That's all I did. It was like I just took this and I solved for T. So these are actually equivalent to each other, of course, on their domains. So we need C divided by P to be positive. And of course, because we're talking about prices and costs, we know that P and C are actually supposed to be positive to begin with. So our C of T function, even though it looks like this when we graph it, it's actually really just this part of the graph. Well, actually, the cost is actually maybe I'm wrong about that. Since C is positive and P is positive, the C values are all positive here. But we're also, I guess, assuming that T is positive as well. So we're assuming that this is the price at time T equals 0, and that we're moving forward in time. So 1 year later, 2 years later, 10 years later, that's what we would use this equation for. Now, if you wanted to move backwards in time and say, okay, if my price now is, $24.95, and there was a 5% inflation rate, what was my price last year? I guess you could use this function to find your price last year. You would just evaluate this at time T equals -1, which would just be P divided by 1.05, and then you would get this value. So I guess technically we could use this for negative values of T. But I guess my point is with the appropriate domain and range, these equations are equivalent to each other. It's just like taking y equals 2x and then solving for x. You say if y equals 2x, then x equals 1/2 y. Those equations describe the same set of points. So technically they're not inverse functions. But if I choose, instead of graphing C on this axis and T on this axis, I can graph T of C on this axis and C on that axis. If I choose to do that, then they are inverse functions. So then I would have T as a function of C here. C is that cost in the future. And this logarithm is the inverse of this exponential function. So when I graph it, it's going to look like this. the function will be 0 when c divided by p is 1. So this is going to cross the c axis at p, because we have p divided by p, which is 1. Log base 1.05 of 1 is 0, because 1.05 to the 0 is 1. And this is giving me the estimated number of years at which a product that was initially priced p at time t equals 0 will cost a certain number of dollars. So I'd say, okay, if my price is, let's say if the price of an oil change is $24.95 now, and that's a great price because that's not typical at all. So when will the price of an oil change be, let's say, $50? When will it approximately double? Say, well, in order to find that, I would just evaluate t at 50. So it's going to be log of 1.05 of 50 divided by that 24.95. That's about 2. And so we would have, here's my 25-ish, and here's my 50. And the y value there is going to give me some number of years. And I would need a calculator for that. But basically, I'm asking myself, okay, remember whenever you're evaluating a logarithm, you're asking yourself a question. 1.05 raised to what power equals 50 divided by 24.95? Notice that that's just a rearrangement of this equation. I could have answered that question by just substituting c of t equals 50 here, knowing my p is 24.5 or 24.95, $24.95, and then just solved that for t by dividing both sides by p and then taking the log base 1.05 of both sides. So we're asking ourselves this question, well, what is the value of t that gives us this? And we know that this is approximately 2. Well, when is what does t have to be so that 1.05 to the t is approximately 2? Like, I don't know. I'm not really sure. So let's use the calculator to find out how many years it would take for us to have a price of $50, or basically, when will the price of the oil change be $50 if it's actually $24.95 right now? So if I take my function t sub 2, which looks like that if I graph it on the same grid, and I evaluate at c equals 50, I get a value of 40.25 or 14.25. And you say, well, what does that mean? That's not $14.24 or 25 cents. That is 14.25 years. So about 14 years from now, 14 years and 3 months from now, approximately, the price of the oil change will cost $50 as opposed to costing that $24.95. According to our model, provided that we have that 5% inflation rate. Now, one of the assumptions that we made at the beginning of the problem statement, or that was stated at the beginning of the problem statement, was that this is provided that the average rate of inflation over the course of 10 years is 5%. Well, this is saying 14 years from now, the price will be, the price of that oil change will be $50. And you might say, okay, well, that's nice. But that model might not be appropriate after that 10-year window. That model might not actually be appropriate during the 10-year window if it's a bad model, if it's not based on sort of accurate observations. But provided that the model is accurate and provided that we continue to have that average annual inflation rate of 5%, it would take, in 14 years and 3 months, the cost of the oil change would be about $50. And of course, we can always graph that point. That's represented by this point on the curve. And then we can also, if we had chosen to, we could have thought about that the other way. We could have said, okay, what does t have to be so that c is equal to 50? Then we'd say, I don't actually know. How can we type this? So I know I want my, oops. Sorry about that. Something happened to my camera. So with this one, we would have c equals 50, right? And that is the y value on the graph. And the t value is, well, it's c divided by p, right? So 50 divided by p. And then we take log base 1.05 of that number in order to get t by itself. And so you still get that 14.25 and the 50. But again, the way you want to interpret this on this graph is the t value is the first coordinate and the cost after t years is the second coordinate, given that average annual inflation rate, provided that that model still holds 14 years from now. And then if you switch the ordered pairs, you get the function values on this graph. But notice that whenever I solved for t, basically I had to use that inverse function anyway. Getting t by itself essentially led to this result. So we're using inverse functions all the time, even if we're not thinking that we're using inverse functions. And whenever we solve for x or solve for t or solve for some independent variable, in some sense, we're using an inverse function, provided that the function actually has an inverse. And if the function doesn't have an inverse because it's not one-to-one, then we are essentially looking for, like, it's basically like you have an inverse relation instead of having an inverse function. So you switch the roles of x and y, and some of your x values have more than one y value. And if you have some x values that have more than one y value, you're usually looking for all the y values that correspond to that particular x value. So then we don't call it an inverse function, but it is sort of an inverse relation because the x and y are just interchanged. All right, so that's how we can actually use inverse functions in real life. And again, we do that every time we solve for t. But I do want to emphasize that technically, if you have t equals this function, t equals log base 1.05 of c divided by p, and c equals p times 1.05 to the t, those are actually just two ways of describing this green curve. But if we choose to use the vertical axis for t of c, and then the horizontal axis for c, if we choose to sort of switch how we are labeling that independent variable and the dependent variable, then it actually does turn into an inverse function where the ordered pairs flip and you see that symmetry across the line y equals x, like we talked about in our section on inverse functions. There's y equals x, and we know all the points. I have a point AB is on this graph, a point BA is on that graph. But that is just one example of how we use inverse functions in daily life. We can be careful. In an application, you don't actually want to switch the c and the t, because then the answer won't make any sense. You really are just solving for the independent variable in terms of the dependent variable. And the equations are technically equivalent to each other. Well, I was going to do several other examples with you, several other financial examples, but I think it's probably a good place to stop here. So we'll end with this example. We'll do other examples in another video. But it's just a very simple model describing inflation, and it may or may not be accurate. And I know that that oil change price isn't accurate, but it does give us something to work with, something to interpret, and then another excellent real-world example of an inverse function.